Assalamu alaikum, my name is Saeed Mohammad Ali Rizzi, and this is the activity for knowing Bayes rule, probability in statistics. Before coming to for the discussion of Bayes rule, let's talk about Thomas Spies. He was born in 1701 in London. He was the person who formulated the Bayes theorem, which is essentially named after him. Unfortunately, he couldn't publish it during his lifetime, but it was published after he passed away. Bayes' theorem is very crucial and important because it provides us with a systematic approach for incorporating new evidence. It essentially a proper statement of Bayes' rule would be that it provides us with a new way or a way to update our beliefs based on the arrival of new and relevant pieces of information. Mathematically, simply put, it could be written as this: is the same mathematical expression as before, where probability of A given B and probability of B given A are the conditional probabilities. Basically, the likelihood of an event occurring given another has occurred, and probability of A and probability of B are essentially the marginal probabilities, right? Now let's just suppose that instead of A and B we have X and Y, and in the first case scenario, let's assume that X and Y both are discrete random variables, right? Then the mathematical expression would simply be probability of X given Y, such that X takes on a value small x and Y takes on a value small y, is essentially equals to probability of X given X. Probability of X takes on a value small x into probability of Y given X upon probability of Y, right? Probability of X takes on a value small x and probability of Y takes on a value small y. These are essentially the marginal probabilities, right? But what if both X and Y are continuous random variables? Then what essentially happens is that um, instead of PMFs, probability mass functions, we would simply change the same expression into PDFs, right? We will describe those continuous variables using PDFs, and otherwise the whole expression would remain the same, right? So now moving on, um, the the example which I have chosen for my presentation is when X is a discrete random variable, where and Y is the continuous random variable, right? So in this case scenario, if X is a discrete random variable and Y is a continuous random variable, and we want to um, find out X, which is the discrete random variable, given we know or we have measured Y. So in this case scenario, our mathematical expression would be this, right? Which essentially indicates that we this is the probability of X given Y, where X takes on a value small x given Y has some particular value, and since Y is a continuous random variable function, so that's why we are using its probability density PDF, right? So the example here which I'm going to discuss here is that the same which we have discussed in class also. It is that such that X is suppose X is a bit which we want to send to some receiver end, right? Which we want to transmit, and let's say X is 0, and X could be 0 or X could be 1, and let's just assume that the probability of X being 0 is, for the sake of simplicity, it's 0.5, and X being 1 is also 0.5, right? But let's say at the transmitter end, at the receiver end, uh, we are receiving a signal which is Y. It essentially is equals to X plus some noisy continuous function which could be either Gaussian. So let's just take Gaussian for the case scenario, which is G. Uh, so what essentially is this formula indicating us, right? So this formula is essentially indicating us that if only we have a continuous noise model, which is essentially PDF of Y given X, we can infer that, for example, if we are receiving some value at Y, and we need to find what could be the value of X for that particular Y, we can use our model for that and the marginal probabilities of X and Y, and we can easily find that, right? So let's just suppose that this is the conditional PDF of Y given X, and this is Y. So let's suppose that we are given our model, right? Which is essentially the conditional probability density function of Y. And let's say for a particular value of X, let's say X is equal to 0, our model essentially gives the outcome this. And for a particular value of X is equal to 1, our model gives the outcome this, right? So this is for x equals to 0, and sorry for the bad handwriting, and this is for x equals to 1, right? So essentially what this formula dictates us is that if we know the model of y, which essentially is like that, if we know that for a particular value of y that we are receiving, what is the probability that it is based on that particular value of x, right? This particular value of x. So if we know this model, mathematical model, we can infer the value of x, right? Because if we use the initial definition of Bayes rule, that our initial beliefs or initial probabilities would now be different. So the probabilities of x being is equals to 0 or being is equals to 1, that would be different according to this formula, right? Which essentially is based on our model of y, right? So if we know our model, and if we know the marginal probabilities of these x and y, we can marginal probability of x and marginal probability density function of y, we can find the or infer the probability of x given we have received a value y, right? So I hope you have understood it. Thank you.